Okay, let's dive into this. Welcome to The Explainer. Today, we're taking a seriously fascinating journey right into the heart of unpredictability. We're going to explore exactly how engineers and mathematicians manage to find hidden order within random, totally chaotic signals. Whether we're talking about a voice signal, the crackle of radio static, or wild fluctuations in a complex system, we are going to walk through the exact mathematical formulas that let us process these random signals.
I know. It sounds like a total paradox, doesn't it? I mean, how do we tame something that is, by its very definition, unpredictable? How do we move from observing pure chaos to actually measuring it, filtering it, and adapting to it? Well, the secret lies in leveraging the laws of chance and probability to build rigorous, concrete mathematical models.
And this brilliantly illustrates what we're talking about. See the horizontal axis there? That's time. And those different wavy paths, zeta 0, zeta 1, zeta 2, those represent what happens when a random process generates multiple possible outcomes, or what we call realizations, over time. We obviously can't perfectly predict any single path's instantaneous value, but by looking at them all together, we can actually start to define their statistical properties at any given time t.
So here is our mental roadmap for today. We'll start by taming random signals. Then we'll look at power spectral density, filtering those signals and finding the optimal Wiener filter. We'll wrap up with adaptive algorithms like LMS and RLS, and finally, practical spectral analysis. It's a structured, steady climb from basic probability all the way up to complex filtering. So stick with me.
All right, part 1. Taming random signals, the foundational statistics. To actually analyze these instantaneous, unpredictable values, we absolutely have to build a mathematical foundation. Let's look at the first-order statistics. First up, the cumulative distribution function, or CDF. This defines our probability, basically the odds that a random variable lands below a certain threshold. Taking the derivative of this CDF leads us right to the probability density function, or PDF. From that PDF, we pull our moments. Think of the mean as kind of the center of gravity for the chaos, which we find by integrating all possible values. And the variance? That measures the actual spread of the chaos around that center. But signals exist over time, which brings us to second-order statistics. Here we compare two different times, t1 and t2. The statistical autocorrelation function reveals how closely related the signal is to itself at those two distinct moments, and the autocovariance does the same but accounts for the mean. These formulas are absolutely crucial because they give actual structure to random vectors. Now, to make any of these formulas actually useful over time, we rely on a massive assumption. It's called stationarity. Strict-sense stationarity means a random process has probability properties that are completely invariant over time. Basically, the probability density right now is exactly the same as it will be 10 minutes from now. However, in the real world, we usually just rely on second-order stationarity, which you'll often hear called wide-sense stationarity. This simply requires that the mean is constant, the variance is constant, and the autocorrelation only depends on the time difference between 2 points, rather than the absolute time.
Moving right along to part 2, power spectral density, where we shift into the frequency domain.
So let's shift our focus to the frequency domain to really understand how a signal's power is distributed. Let's trace exactly how we derive power spectral density, or PSD. Step 1 is windowing. We isolate a specific time window of our random signal and calculate its Fourier transform to get the periodogram. But because the periodogram itself is random, step 2 is averaging. We calculate the statistical average of these random spectral densities, which brings us to the correllogram. And finally, step 3 is the incredibly elegant Wiener-Khinchin theorem. This states that the power spectral density of a wide-sense stationary process is simply the Fourier transform of its statistical autocorrelation function. It's this beautiful, direct bridge between time and frequency.
Which brings us to section 3, filtering random signals through linear time-invariant systems.
Let's visually anchor this input-output relationship to see how these stationary signals behave when pushed through a linear time invariant, or LTI, filter. We've got our unpredictable but statistically defined input random signal, x of t, passing through our deterministic filter, resulting in our filtered output, y of t. As the signal passes through, its statistical properties are fundamentally mathematically transformed.
So, the crucial point here is exactly how they transform. The expected average, or output mean, simply equals the average of our input multiplied by the continuous gain of the filter. For the power spectral density, the output PSD equals the input PSD multiplied by the magnitude squared of the filter's transfer function. And if we look at the cross-correlation between the input and output in the frequency domain, the interspectral density equals the input PSD multiplied by h of f.
Next up, Section 4, the optimal Wiener filter, minimizing the error.
This right here is the ultimate mathematical pursuit. We're looking for the absolute perfect filter. Let's trace this equation-by-equation derivation. Our goal is to minimize the mean square error, or MSE, between our observation and our desired target. To minimize this error, we cancel the gradient of the MSE. This leads us directly to the orthogonality principle. The expected value of the observation matrix multiplied by the error absolutely must equal 0. By setting that to 0, we derive the famous Wiener-Hopf equation. Take a second to appreciate this one. The autocorrelation matrix of the observations, multiplied by the optimal filter weights, equals the cross-correlation vector. Therefore, our optimal Wiener filter simply equals the inverse of the observation autocorrelation matrix multiplied by the cross-correlation vector. It is, honestly, mathematically perfect.
All right, Section 5, Adaptive Algorithms, LMS and RLS. But, here's the real-world catch. Inverting that massive autocorrelation matrix we just talked about, it's computationally heavy and sometimes literally impossible to do in real time. So we have to transition to iterative algorithms that approximate this optimal filter on the fly. The most common method is the stochastic gradient algorithm, widely known as LMS, or least mean squares. It's a brilliant 4-step cyclical recipe. Step 1, we initialize the filter weights to 0. Step 2, we calculate the filter output. Step 3, we calculate the instantaneous error. And finally, step 4, we iteratively update our filter weights based on that error using an adaptation step factor. It is constantly correcting itself.
Now let's compare those straightforward LMS update equations against its heavier counterpart, the recursive least squares, or RLS algorithm. LMS is wonderfully simple, but its convergence can be painfully slow if the initial data is poorly conditioned. RLS, on the other hand, essentially uses Newton's method. It actively tracks an inverse matrix, updated via a complex formula where the new matrix equals the old matrix plus a correction term. The filter update relies heavily on this matrix, allowing RLS to converge extremely fast, entirely independent of bad initialization, though, for sure, at a much higher computational cost.
Now, what's really interesting about this slide is the structure of the matrices we've been referencing, particularly the correlation matrix. When you chart out the expected values of the time-shifted random variables, you get this beautiful symmetrical structure. Notice how each diagonal is composed of identical elements. This is known as a Toeplitz matrix. By subtracting the squared mean from these elements, we instantly derive our covariance matrix. Recognizing these repeating mathematical patterns is exactly what makes all this complex processing possible in the first place.
And that brings us to our final section, number 6, Practical Spectral Analysis, Theory in Action. Let's bring all of this heavy math back down to earth for a second and see the theory in action. In reality, calculating a single periodogram for a random signal is just way too noisy. So we use the average periodogram method. We take our long sequence of sampled data, break it up into overlapping sections, apply the fast Fourier transform algorithm to each section to get individual periodograms, and then simply average them all together. This smooths out the randomness and gives us a highly reliable estimate.
Building on that, if we just arbitrarily chop our signal into chunks using a standard rectangular window, the math creates these disruptive side lobes in our frequency analysis, specifically due to the sinc function. To overcome this in the Corey-Lellegram method, we multiply the time signal by a weighting window, like a Hamming or Hanning formula. These windows gently taper the edges of the signal down to 0, smoothing out the data before we calculate the autocorrelation and apply the Fourier transform. It's a mathematically elegant way to clean up our real-world signal.
So what does this all mean? We've covered some incredible ground today, from deriving first-order statistics to calculating the optimal Wiener-Hopf equations and designing adaptive LMS filters. But I want to leave you with one final provocative thought. All these powerful formulas heavily rely on the assumption of stationarity. But what happens to our systems when the very nature of that unpredictable signal shifts beneath our feet? Well, to capture those complex dynamics, engineers turn to parametric models like autoregressives or AR processes using the Yule-Walker equations. They use moving average, or MA, and even combined ARMA processes. Exploring how those specific models handle shifting unpredictability is the absolute bleeding edge of this field. Thanks for joining me on The Explainer.